Today I want to talk a little bit more about calculating electric potential using a path integral. We're going to be talking about how to set up the path integral and when is appropriate to use it. But before we get into that, I want to talk a little bit more about how to find the work done on an object. So from last year, if we were pulling a box along the floor or the ground, and we were applying a force FA in this direction, let's say that it's frictionless just for argument's sake here. It's going to accelerate to the right with some acceleration. Let's say also that the object travels a distance d along the x direction. If I wanted to try to find the amount of work done by this applied force over the distance d, I would say that the work is equal to, what I would have to do actually is find the component of FA that's in the direction of the displacement. So here it's Fx. And the work done is simply going to be Fx times d. Now what's Fx? If this was given as an angle theta, Fx would be Fa cosine theta. So the work becomes F d cosine theta. This is because work is actually a dot product. So work is equal to F dot d. If you'll recall, the dot product is a way to multiply vectors together and to get a scalar. The dot product is really sort of a measure of how parallel two vectors are. So when Fa and d are parallel, we're going to get the maximum value of work. Let's look at a slightly more complex example. Let's say that I have a non-uniform electric field. Say it looks like that. And I want to see what the change in potential energy is from, let's say I'm going to name this point as my reference point. This point is my reference point A. And I want to know how much potential energy it has at B with respect to A. What I'm really asking is how much work did it take to get from A to B? And I don't even really have to take a straight path from A to B. I can take really any path I want. Now what I'm going to do is, for this problem, I can't really use this formula anymore, this work equals F dot D, because the force is not constant anymore. So what I can do is break up this path into infinitesimally small pieces of the path, each of which I'm going to call dl. And what I'm going to do is I'm going to try to find how much little bit of work is done over each of the little pieces of dl. And then I'm going to add up all those little d works. So at every point on the path, there's a different force exerted on the particle according to the value of F of the electric field E. So, for example, at this place along the path, there is a force Fe on the particle. And in order for me to move it from A to B, I need to apply a force to counteract Fe. So those are the same in magnitude and opposite in direction forces. Meanwhile, I'm traveling a little bit of dl, which I'm going to represent as a vector like this, dl. So in order to bring this charged particle a little distance dl, I'm going to get that the little bit of work that it takes is equal to negative Fe dot dl. I put the negative in there because Fe is pointing this way, and the applied force that I have to put on the charged particle is Fa. It's exactly 180 degrees, and that's what makes this negative Fe. To find the total work that it takes to bring it from A to B, we're going to integrate. We're going to add up all those little dW's, and we'll integrate both sides. So this is going to go from A to B. So another way of writing this will be that the electric potential energy at B with respect to A, so that's, pay attention to the order of this subscript. This is the potential energy of B with respect to A. So we're saying that at A, the potential energy is 0. That's going to equal negative the integral from A to B of Fe dot dl. This is what we call a path integral or a line integral. Well, so far we haven't really talked anything about potential. So how do I turn this formula into something that has to do with potential? Well, remember that the definition of potential is the electric potential energy per unit charge. Also remember that the electric field is defined as the force per unit charge. So what would happen if we divided both sides by Q, by a charge? Well, what I would get on this side is V, the potential of B with respect to A, is equal to negative the integral from A to B of E dot dl, since F over Q is going to give us E. And this is the important formula that we're going to be using today. So when do we use this integral? Well, in order to use this integral, it's really important that we know what the electric field is and that we have a function for E. So when are the times that we know what E is as a function? Those times are the same times that we use Gauss's law. Let's look at an example. Let's say that I have a sphere of charge. I'm just going to call that charge plus Q. And I want to know, let's say, actually let's have this as a goal. Let's have the goal be that I want a graph of potential as a function of R, where R is the distance away from the center. I'm going to say this sphere, let's say that it's a conductor. And it has a radius big R. So there's going to be a break probably in our function at capital R. So I'll draw that in there. What does the electric field look like here? Well, if it's a positive charge, the electric field will be going radially outward. I'll just draw a few lines. These lines should really go all the way around, but I'll just draw a few in. And I want to know, I want to pick a point. Let's say I pick a point here. This is a point P, and it represents just any point that's outside of the sphere, a distance R away from the center. So when I say that we're looking for the potential, that's not quite a complete statement, because what Well, there is no such thing as an absolute potential. What there is a potential with respect to some point where the potential energy equals 0. So in this sort of situation, we're going to assume that potential energy is equal to 0 at infinity. So we're going to take a path that goes from infinity, so this is A at infinity, and it's going to go to point B at point P, just to make the analogy to the way we had written the formula earlier. So what I need to do now is choose a path from A to B along which I can calculate the work. I can choose any path really. The work should be the same since we're only dealing with conservative forces. So would it be a good idea to pick a path to be like this? And the answer to that is of course not, because what we would have to do is we would have some force here that's going this way, and our applied force would have to be in this direction. Our path dl is in this way. So we'd have all sorts of angles. So that's not a good idea. So what we should do is pick a path that goes along an electric field line. If I pick a path that's along an electric field line, then my dot goes away. So if you'll remember, the potential of B with respect to A is negative E dot dl from A to B. Well, we know what the electric field is. It's 1 over 4 pi epsilon naught Q over R squared. We know that from Gauss's law. And that's true everywhere along this path. So even if we broke this up into little dl's, that's going to be true along the path. Our dot product goes away because our dl and our applied force are in the same direction, and we multiplied this by dl. These are magnitudes now. Now our integration variable is dl, but we want to change that to be something that we can set limits to. So what I'm going to do is turn this dl into a dr. Now r is going to be the distance from the center of the sphere to some random dl out here. So if that's going to be r, then if I chop that up into infinitesimally small values, those are going to lie along the same line as dl. So I can actually just substitute, since dl is just a length at this point, I can substitute dr for dl. So this here is going to be equal to negative the integral of 1 over 4 pi epsilon naught Q over R squared dr. Now that we're in dr, we can set some limits of integration. Our path is going from infinity to R, this R that goes to point P. I hope you're not confused by this is my integration variable, but it's also the limit. Okay, so probably what I should have done is called this R naught and called this big R, so that we'll go from infinity to R. And this would be R. Okay, so now if you perform that integral, what you're going to get is 1 over 4 pi epsilon naught Q over big R. And I'll let you do the math on that yourself. So what that says is that out here in our graph, this is going as 1 over r squared. So I'll kind of draw in that sort of thing. This is an inverse function, 1 over r. And we kind of have to figure out still what's going to be on the left side. But I know that this has a maximum value here of 1 over 4 pi epsilon naught q over r naught. Now, by the way, it's worth mentioning here that this function that we used, we got this through Gauss's law. So we couldn't have done this if we didn't have the function that we found through Gauss's law. So that's really important. Okay, now we have to find out the potential inside the sphere. So let's pick a different point P. And this is our new capital R value. And we're going to have to do another integral. This time you have to notice something. And what you notice is that the electric field is actually different on the outside than it is on the inside. If you remember from Gauss's law, since this is a conductor, we're going to say that the electric field inside of here is 0. But we have to break this integral up into 2 parts. Let me scroll up a little so you can see the diagram a little bit better. So we have to break this path up into 2 parts, or at least the path integral up into 2 parts. So here we're going to have VBA, the potential at B with respect to A, where A is at infinity, is negative the integral of E dot dl on the outside plus negative the integral of E dot dl on the inside. What happens here is that since on the inside the electric field is equal to 0, this goes away. The other integral, the first integral, is going to be negative integral from infinity now to r naught. We're going from here to the surface of the sphere of 1 over 4 pi epsilon naught q over r squared dr. This is simply going to be, I'll write it a little lower, V inside is going to be equal to 1 over 4 pi epsilon naught q over r naught. The interesting thing about this here is that there is no r, big R, that shows up in this equation. Therefore, this value, the potential on the inside, is just constant. That's kind of weird. So let's plot that first. This becomes this graph here. Now, how does that make any sense? Well, it takes a certain amount of energy to go from infinity to the surface of the sphere. That's 1 over 4 pi epsilon naught q over r naught. But then once you're inside the sphere, there's no force on the charge inside the sphere since the electric field is 0. Therefore, since there's no force on the inside, then it doesn't take any work to move the charge around anywhere inside that sphere. To get the particle to any point P inside the sphere, it only takes this amount of work, 1 over 4 pi epsilon naught q over r naught. And then once you're inside, you don't have to do any additional work. So I hope this cleared up how to use the path integral in order to find potential. And remember, it's easiest to use this method when we know the function for the electric field. So that means that we probably want to use it in situations where we use Gauss's law. Then always pick a path that's easy. So either it's parallel to the electric field lines or it's perpendicular, in which case the integral will be 0. So just to recap the situations in which you would use this path integral. So basically you're going to use it for a sphere, for a cylinder that's infinitely long, or for an infinite plate. If you have any questions about this, please write them down and bring them to class. See you there.